Yeah, welcome everybody. We are in the chapter about NoSQL databases. Can you hear me? Can you see me? Please write hello in the chat because I'm using a different setup today. I'm at the university today and not in the home office. Unfortunately, I cannot use cannot show your chat messages today, but I will simply copy and paste them to an editor, and then that will also work. Yeah, NoSQL databases. We took a look at key value stores. Can you hear me well? Is the microphone working? So we took a look at key value stores, for example, Redis, white column stores, HBase, and then MongoDB. And now we are talking about graphs. Today, to finish this chapter about NoSQL databases, we take a look at Neo4j, that's a graph database, and 2 graph languages. And then the next big chapter is more about graphs. So this week and next week and upper next week and so on. So in next week is no lecture because it's holiday. But the next 3 or 4 weeks, no, 3 weeks, we will talk about graphs, and graphs. Yeah, and Neo4j is a graph database. You store vertices. In these vertices, you store your data. For example, a person vertex has first name, last name, and so on. And then you have edges with which you can connect the vertices. Vertices in a so-called property graph. So we call it a property graph. The graph model is a property graph, meaning that a vertex has a label, basically the type of the node, and a set of properties, first name, last name, and so on. And these properties are arbitrary key value pairs. For example, this vertex here has the type person, and then a set of properties. The name is Peter, city is Berlin. And edges are directed connections between 2 nodes. So we always use directed edges. So when this is a node and when this is a vertex, this is an edge to another vertex. And edges are directed edges when they have an direction, when they have an arrow, when they are an arrow. It's also possible to have graphs with undirected edges, but not in Neo4j. In Neo4j, every edge has an incoming node and an outgoing node. And I use the word node or vertex. It's the same. So an edge connects 2 nodes and they have a label. So this edge here could have the label friend and so on. So it's directed. And an edge can also have properties. And here's an example friend connecting 2 vertices. I simply wrote the vertex in it's just an anonymous empty vertex. It doesn't matter what this vertex is. I just want to focus here on the edge. So this is the edge. It goes from this vertex to that vertex and has the label friend. So it means that this vertex has that vertex as a friend. And then a set of properties, and here I have one property: since when are these 2 people friends? Yeah, so as a graph it could look like this. two vertices with the same type, person, this is a person, that is a person, this is Peter, this is Jane, and they are friends, and the direction of the edge just doesn't mean anything. It could mean, okay, Peter sent the friendship request to Jane or so, but maybe not. So the direction is simply not of any interest. Peter has one friend, Jane, and Jane has one friend, Peter. So if we want to find all friends, we have to go to the friend neighbors via a friend edge, independent whether this edge is an outgoing one or an incoming one. Neo4j uses as a language Cypher. And Cypher is very similar to SQL. Before I want to go to detail about the Cypher language, I first of all download Neo4j. So neo4j.com. It's an open source database, but there are also other versions which are not for free. Experience on your desktop. So the desktop version is the one that I need for my laptop. And then enterprise server. This is for big enterprises. Community server, that's better. Community edition is the simple edition to try out Neo4j. And then, yeah, both versions for Linux, Mac and Windows are simply archives. So I download the tar archive for Linux now. Username Neo4j, password Neo4j. This can be important. I unzip it. This was not really unzipping. So now I have it here. Here we have a bin folder and a conf folder and a data folder. Databases is empty, so Neo4j will store its data in this folder here. And in this bin folder we have things that we can execute, but we are not clicky bunty users. We need a terminal. So now in this terminal I go into the bin folder and there is Neo4j. And I say now Neo4j start. Started Neo4j, so it's now running at process ID 78911. I have to write Neo4j stop to stop it again. And start to start it again. So started Neo4j, it is available at localhost 7474. So we talk with Neo4j via HTTP. This is really nice. Our clients, when I would now write a Java application or a Python application to work with Neo4j, I simply have to configure the host being localhost and port being 7474. And the nice thing is that Neo4j has a web front end. So I open it in my browser, and username is Neo4j, password is Neo4j, as we saw on the download page here. And that's it. Now I'm connected. And now it's good if we Neo5j. I have to change the password. So now we need to no Cypher. The from clause in SQL is the match clause in Cypher. The idea is we match something in the graph, but before that we need a graph because currently we don't have data. We can use this example vertex here and this example edge. I can say create and then a person. I call it P, like Peter. This is not important. This is not stored in the database. So there will not be a P. This is like in SQL from people P. This is just an alias that I give this node. And you will see why I introduced this alias, because I create another person. The alias is J. Her name was Jane. And I create a vertex. So from P to J. And I give this vertex the label friend and properties since is 4th of May. Okay, Control Enter. Invalid input, expected white space here for the name. This is not equivalent to JSON. No, invalid input for the edge. Here the box bracket is missing. So the edge properties are written into box brackets and the edge label. Control Enter. Okay, added 2 labels. One label is person, one label is friend. So they are stored somewhere in a label store. They were added because there is no person vertex already and no friend edge yet. Then created 2 nodes, the Peter node and the Jane node. 5 properties, name, city, since, and 1 relationship. Okay, now I can look in my graph, match. I want to see the nodes. Let's call them X, return X. So this is now my graph. I didn't say I'm interested in the edges in my query, but if my query finds 2 nodes and there is an edge between these nodes, then the edges are also displayed. So this is basically the select star from query of Neo4j. You search for a pattern in the graph. This pattern means a vertex. Normal parentheses are always vertices. And then I return the vertex in this case. When I display it as a table, you see that the edge is not part of the result because I return the vertex, and the vertex has an ID, a label, and a set of properties, and then this other vertex has other IDs, labels, and properties. But in the visual representation, Neo4j displays also the edges between my result nodes. Yeah, and this is the idea of Cypher. I specify in the match clause a pattern, and I search for this pattern within the graph. Within this pattern, I can use aliases or variables, and then I can say where x dot name is Peter or something. And then I find, so I filter the ones with this where predicate. Or I say I'm not interested in the nodes, I'm interested in the names of the people. And then the result is a result set with strings. Okay, let's take a look at more examples now. So the match clause, that's the most interesting clause in Cypher, is pattern matching within the graph. I search for a pattern. For example, this pattern here, I search for this node, and this node has an edge to another node, and before the colon I can introduce my variables. After the colons I can specify the node type. I didn't do that here. Here I don't have colons, but I could say I'm only interested in person nodes. Yeah, my graph is very boring. There are example graphs, movie graph, play movie graph is a magic command that that creates a lot of movies and actors. This is good for playing around. Okay, here's now my graph. Now again I can say match x, return x, and now I find a lot more. And here are still my two person nodes from before, but here are many other nodes, and nodes with different labels are visualized with different colors. For example, the blue nodes here are of the type movie, and the orange ones are person. And then there are red nodes, person in lowercase. These were the two nodes with Peter and Jane that I created before, but they are of course not interconnected with other nodes from this graph here. So we store everything together in one big graph, and the main difference between the nodes is their label. So what tables are in SQL are labels in Neo4j. Then I can find all movie titles, match M like movie of type movie, return M returns these movies as a set of nodes, set of vertices. There are no edges between them, so we don't see edges here. Or I use, what do they have for properties? Released title. Return m.title. Shows me all titles. And when I say give me all people, no, person. Give me all persons. Persons have name, and I take Tom Cruise. So give me the ones where p.name is Tom Cruise, and I make a more complex pattern in the match clause. I'm interested in all movies that Tom Cruise plays in. So we have friends, we have acted in, and then we need a movie node. So this is my pattern I search for. A person node should have an edge to a movie node. I give this person node a variable p because I want to use it later on in the filter predicate, in the where predicate here. I don't give this edge a variable. I can do this, but I don't need it because I don't make a predicate or something there. But I give the movie a variable m because I'm interested in the movie titles. So this is basically a query: in which movies did Tom Cruise play? Yeah, these 3 movies. Yeah, I just want to give you the idea of how to work with such a pattern matching language like Cypher. We search for a pattern in the graph. Within this pattern, we use our own variables, and we can then use these variables in the where clause, order by clause. We can use limit, return. We can use update to not show something but change something in the graph. We saw the create clause to create new nodes. Yeah, these clauses are very similar to SQL. The big difference is the match clause. There we search for a pattern within the graph. What's this query here? I search for a person, let's call it P, and then a friend. Here you don't see any arrow symbols, no greater than, smaller than, like here, acts in, this was written as minus arrow, so it transforms it into an arrow symbol here. This is an outgoing edge from person to movie. Here I say the direction isn't interesting for me. I follow the edge independent of its direction. So I find other people that have an outgoing friend edge from the one that has the name Peter, and those which have an incoming edge from the node with the name Peter. Then I order it by the friend's name, and then I return the name and the city. So, question for you, go to frage.de, Frage with 2a, and please give me the answer. How are the values p and x stored within the database? Are these internal node IDs? Are these properties? Are these labels? Or are they stored nowhere in the database? When at least 25 people have answered, I show the solution. Please go to frage.de and answer the question. Okay, 2 more please. I already said the answer. They are stored nowhere. You are absolutely correct. These are no internal node IDs or something. This is like in SQL, the clause select p.name from person p, where p.age is 25 or something. So this is also not stored in the database. I can call it as I want. This is just for me to refer to that, in this case, node and this node. Yeah, do you have questions about Cypher? So I just want to give you the idea behind Cypher. We will not make thousands of examples here. you should have seen the language Cypher, and that's yeah, and understand the idea behind that you search for a pattern within the graph and then continue like you would do in SQL. Make filters on the nodes and edges that are found there, order the result, return the result, make updates, create new nodes, create new labels, create new edges. Do you have questions? Will we have to write queries in the exam? One possibility would be that I give you a query and you tell me what this query is about. Or I give you a query and it has gaps and you have to fill the gaps. Or I give you a query and you have to modify the query. So it's not necessary to know Neo4j by heart. So you have to understand Cypher. That's more important than to know everything. It's good to try out many parts of Cypher, make your own queries. Then I'm very sure when you write queries on a database, try out how to do things on this movie database and so on, then I'm sure that you can answer the question in the exam. And I have to tell to you, the chances are now bigger that it actually will be a written exam. So I said I would like to have an oral exam, but the number of participants is more than 100, and this makes it impossible to make an oral exam. But it's not finally determined yet. I just want to tell you that the chances increase that it will be a written exam. But you don't have to know everything in all details. You don't have to write Python programs, no complex Cypher query, no complex SQL queries on JSON data. You have to understand these concepts. And that's my challenge for me to make a good exam, to check your expertise in these concepts and not in how good you learned all the single facts. Is there a limit to the number of nodes in the match part? No, the match part can be as complex as you want. So, but when you really want to use Neo4j, take a look at the language specification, because you don't make queries like, oh, give me a person and then a friend, and then a friend of the friend, and a friend of the friend of the friend. There is an abbreviation, I think it is friend times 2 or something. I'm not sure. I'm a certified Neo4j developer, but I'm currently not sure what the exact syntax is. So, and I want to find all friends of friends. I think this is valid. Otherwise, there would be an error because I don't have friends of friends. But I can remove this error here, and we go back. So, person in lowercase was our example. Yes. So I want to have p.name and q.name. So Peter has a friend Jane, Jane has a friend Peter, and I think it's friend times 2. No. There is a syntax. You have to Google to find this syntax. But this makes match clauses much shorter so that you don't need to write large patterns. You simply write that they are... I'm not sure about the syntax now. And it's also possible to make from and until here. Yeah, in the chat there comes the recommendation. You could try it on the movies table. Yeah, but in the movies graphs, there's a person that has an edge to a movie, and then another person to have an edge to the same or another movie. So here with the friends of friends, it's nice because a person has a node to another person. This is nice for recursive queries. And I don't know the syntax now of how to specify the length of the edge or the number of edges. I can simply Google Cypher number edges. This find out. Nodes. Relationship types. This type or that type. Here. Times 2. Times 3 up to 5 times 3 dot dot. But I can imagine that, so I think what I had in the very beginning, this was correct, but it doesn't find Peter is a friend of Peter because of some duplicate eliminations or circle avoidance mechanism. Let's create another node. Let's create A is also a person and it has a name N and an edge from P friend A, and then again where I have to find P. P has the name Peter, so instead of using a where clause, it's also possible to use the predicate directly here in the match clause. So I find the node P and I create another node A and another edge from P to A. Only directed, yes, yes, yes. From P, an outgoing edge. Okay. And now again oh no, I wanted to create not from P to N, but from, okay. Then from N to Bob. So to show you what I did here was, I show you the graph, give me all person nodes, return P. I simply added some more nodes in my graph. So now here's Peter. Peter has a direct friend Jane and Anne has a friend Bob. So when I want to now find friends of friends, I would find Peter has Bob as an indirect friend. So here, P has a friend, indirect one, another person Q, give me the name of P and the name of Q. Okay, Peter has Bob as an indirect friend, Jane has Anne, because I follow the direction in both directions, the edges in both directions. So Jane knows Peter and Peter knows Anne, so Jane indirectly knows Anne, and then the opposite direction, Jane, Bob, Peter, like here, the other way around. Yeah, and I could say now 1 to 2. Then I would find the direct friends. Peter knows Jane and Peter knows Anne. And Peter indirectly knows Bob. And then the transitive closure. So up to an arbitrary number. Yeah, this would find all reachable nodes from this node. So Bob has a path to Anne somehow. What is the unique identifier of the nodes? In practice, often there is a ID. So you introduce an ID, but as we saw here in the result table as well, we saw that there's an internal ID as well, identity. So this identity is automatically created when we create a node. This is not like a primary key. It doesn't belong to the properties. It's a special kind of property, the ID. It has to be unique, and this is basically the primary key, and there is an index on this ID to find quickly a node with a given ID. Yeah, we didn't use it in our example here because I always focused on the name property to identify a node. But in general, this identity here is used. Okay. Another graph language is called Gremlin. And Gremlin belongs to no graph database. So Gremlin is a generic language which you can query a graph that is stored in Neo4j, in Tinkergraph, in Titan, so basically all graph databases have a Gremlin interface, a Gremlin, would you say it a driver? No, a Gremlin interface, so that you can talk Gremlin with a database. Cypher is the language by Neo4j, so this is built in, but there's also the Open Cypher project. They open sourced it, the language, to say, hey, other graph databases, if you also want a Cypher interface, here is the specification of the language Cypher, and then you can talk to a Titan database with Cypher as well. And Gremlin has a completely different approach than Cypher. Cypher, the approach was pattern matching, finding a pattern in the graph and then doing something on the nodes and edges that are in that pattern. So iterating over the results of that pattern match. Gremlin is not such a pattern matching approach, but a traversal approach. So take a look at this query here. Find Marco's person node. G.v finds all vertices of the graph. So this is a set. This is the set of all vertices. Then this is a filter operation. So when this set has 1000 vertices, only some of them survive this has method here. So has is then something we evaluate on this set of nodes. So only those that have the label person and the name Marco. There's has with only 2 parameters. It just checks for property and a value, but the has with 3 parameters checks for a label, then a property name, and then the value in that property. So we find in that graph here the person that has name Marco. Yeah, and Gremlin we can also download. Gremlin movie graph. Apache Tinkerpop Gremlin. Tinkerpop is a whole suite of software. Gremlin is just one part of it. It is the language to talk with graph databases. And this language changes so extremely often. So in every release, they change how to create vertices and so on. So again, a zip file. Gremlin console, again a bin folder. Then we have for Windows the bat file and for Linux the shell file. So gremlin.sh. Okay. I could now use commands to say connect to my Neo4j database that is currently running, but it's even simpler to say I work on Tinkergraph, because Tinkergraph is an embedded NoSQL database, an embedded graph store. This means I don't have to run it as a server. It simply runs as a library for this program here. This is developed in the language Groovy, so I can now use the language Groovy commands. I don't know Groovy, but I know some commands. So graph is create the crew. This is a method, a factory method to create this example graph here. So this graph shows we have a person called Marco. He lives in some locations, and then Marco develops a software called Gremlin, and Marco develops a software called Tinkergraph, and here's another person called Matthias, and Matthias also develops software. He does it since 2012. Marco develops it since 2009, and so on. So this is the example graph that is created when we call tinkerfactory.create the crew. On this graph object, we cannot do so many things. This just represents the graph. So 6 vertices, 14 edges. And to talk Gremlin with this graph, we need a traversable object. And in the newest version of Gremlin, it works like this. So half a year ago, you say graph.traversal. Now you say traversal, blah, blah, blah. So that's not important. Important is the idea. The concept behind the language Gremlin is starting with a set of nodes, then filtering, then going to the neighbor node, so navigating through the graph is the idea here. And we do this on this G object. G.v gives us all vertices. Here we see internal IDs, 1, 7, 8, 9, 10, 11. G.e gives us all edges. So there is a develops edge from the node 13 to the node, from the node 1 to the node 13, and this has the edge ID 13. There's a develops edge from the node 1 to the node 11. Let's see if it corresponds to these IDs. Yes, it does. There's a node from an edge from 1 to 11 here. So these are the internal IDs. And we can now filter. So has person should be the label, and then the name should be Marco. This is an empty set. Marco with K. Okay, now we find one vertex. And then I can say values, give me the name. Okay, this is not interesting. Give me the name of the person with the name Marco. So I take all vertices, then only those that fulfill this predicate here. And then values shows me the value in a specific property. What other properties are there? Location. Yeah, and location is a set, so there the property is basically an array. So you see here in the graph, Marco has San Diego, Santa Cruz, Brussels, and Santa Fe. Okay, more complex query, and there we see how graph traversal works. Which software did Marco develop? In Cypher, you would search for a pattern. A person P develops a software S, and then P.name should be Marco, and software.name I want to return. And here we traverse through the graph from node to node. So I start with this node here, Marco. I start with all vertices, then I filter out those that have the type person and the name Marco. So I start on this node here. Then I go via the edge develops to the neighbor nodes. I find this software and that software. And then I go into the property name. So hop by hop, I traverse through the graph. So all vertices, only those that have the label person and the name Marco. Then I go via an outgoing edge develops. And then in the result, this is not really necessary in our example, but it's always good to say, okay, I'm only interested in the neighbor nodes that are of the type software. This is the case for everything. So a person only develops software. There is no node from no edge. Person develops person. But maybe in the future we develop cooking recipes or so, and we don't want to find them, we only want to find software. So it's good in a query to make sure that we only find, in this case, software vertices. And so we find software nodes now. So we start at Marco. Marco develops software, and for this software I want to print out the names. So all vertices, only those that have the label person. I would do this with has label. These are only these 4 from this 1, 2, 3, 4, 5, 6. Name should be Marco. This is this node. Then out goes to the vertex via the edge called develops. This now finds 2 vertices because we have 2 edges. Person develops this and person develops that software. This filter has labeled software, will not change anything because this is true for both. And then I want to know the name of the software. Okay. Marco develops Gremlin and Marco develops Tinkergraph. Okay, there are some questions now in the chat or comments. Are labels and attribute names case sensitive? Yes, yes. Labels and attribute names are kind of data level. Not like in SQL where table names and column names, that would be the correspondence to here, are on the metadata level. Here, labels and attribute names are case sensitive, similar to JSON. Their attribute names are also case sensitive. If I would write, give me not the name, but the name with a capital E, it would not find anything. So the property is called name and not name. Another question, is it possible to return subgraphs yeah, this is a good question. In Cypher, you can return a subgraph. Here we had a query, and then the result of this query looks like that. But this is only nice for me in this browser here, for interactively working with the graph. Imagine how you would develop an application. In an application, you don't want to have a graph as the result of the query. So in an application, you never say return p. In an application, you say return p.name and p.city. City. So the data that is stored in your database is a graph. The query language is a graph query language, which is very powerful and optimized for graphs. But the result is nice to be similar to a relational table. So then you can use a for loop in your Java program and then result set.next, and while result set has next, go to the next row in that result, and in the result set you access the column name and the column city. So this would be my recommendation to work with a language when you develop an application. And it is also possible to get a result set that consists of not strings and integers in columns, but of nodes. And within these nodes, you can then access their properties, their labels, their neighbors, and so on. But you could also do this in the query language. And like I always say, what you can do in the query language, do it in the query language and not afterwards in the application. And in Gremlin, it's more restricted von Haus aus, by house. So it's you cannot return a whole graph here, because you return that what the last operator gives to you. And each operator, so which operators do we have? Has is an operator. Has is a so-called 1, 2, 0 or 1 operator. 1, 2, 0 or 1 operator. Don't know how we write it. So for each node that is in our set, we decide, does it survive that set, that step or not? So like in MongoDB, the match operator. So does this vertex survive this step or not? And out is an 1 to n relationship. If Marco develops no software, then we find nothing. If Marco develops one software, then we find one other node. and if he develops 15 software products, then we go into 15 other nodes. So we traverse through the graph, and the result of the query is the result of the last operation up to this last command here, values. If I remove this, it would be always set of nodes, the data type. This is a set of nodes. The has returns a set of nodes, out returns a set of nodes, has label returns a set of nodes, and after this values here, we cannot continue. It's not possible to do something dot here, because here we have a set of strings. Maybe there are methods that you can use on set of strings. I think you can say max, and then you find the largest value here. Or when you have numbers, then you can say average, and then, but yeah, that's the result of the query. So you cannot return a graph with Gremlin, because in general you want to write a query that gives you a set of strings, numbers, blah blah blah, a result set, and in your application with which you connect to the database, you iterate over that result set like you would do on a result set on an SQL table. A very good point about Cypher in the chat. I had this query where I want to find friends of friends. Peter had Jane as a friend, and I wanted to find indirect friends of Peter, and I wondered why Peter isn't an indirect friend of himself, and the correct answer is the same edge is not traversed twice. That's a very good explanation, and this is true. Yeah. So that was the reason why I didn't find when the graph was so small that Peter is his own friend of friend, because this edge is only traversed once and not multiple times. Here you see out. There's also in. So when I want to ask who developed Gremlin, let's do this. Give me all vertices, and then it should be a software vertex with the name Gremlin. And the nice thing on these so-called pipeline languages, Gremlin is a pipeline language, like the aggregation pipeline for MongoDB. The nice thing on pipeline languages, you can work step for step. Okay, is something found here? Yes. Then I continue. Then I go via ingoing edges. Who develops it? These 3 nodes are the developers of Gremlin, and then give me the name. Okay, Stefan, Matthias, and Marco developed Gremlin. You can do it step by step, and in between you can press enter to see the intermediary result. So in would be another direction, and there's also the direction both. So this doesn't change anything here, but it would be useful for finding friends. So Peter has friend Jane as an outgoing edge. Maybe he has other friends with an incoming edge, and then the both step is good. So we traverse the friend's edge in both directions. We go to the neighbor via both directions. So what does the out step return? So what is the result of the step out? Please go to frage.de. Does the out step return a list of nodes, a list of edges, a list of strings, or a list of labels? So in general, not for this query, but also for this query. So what is the result for this query here? So what does this out method, this out step return? What's the resulting data type? When 25 people have answered, here I can stand, that's nice. Okay, of course it's a list of nodes. Everything is a list of nodes except these values. So some of you answered a list of edges. This makes sense, right? Because I am in a vertex and I go to the outgoing edges. But yeah, Gremlin says out doesn't give you the edge if you really want the edge. So here, where's Marco? This is, as we see, a list of vertices, VVV. You can say out E, then you find the edge. This is only necessary if you're interested in edge properties. So in which year did he develop what is it called, since? Yeah, in which year did he develop something? What's when did he start developing some software? In 2009, so the minimum. When you're interested in edge properties, you use out E to be in the list of edges, but the normal out step goes via the edge in the neighbor node. So in list of nodes is the right answer. Okay, we are finished with this part of NoSQL databases. We took a look at NoSQL in general. NoSQL stands for not only SQL. We looked at the key value store Redis. Redis supports simple and complex value types. Simple value type for key value store is just X is 5, Y is 7, A is hello, and so on. And B is a whole video as a binary format. But the complex type, we had lists, sets, hashes, and there are much more complex type, not much more, but some more complex type for very special use cases. In wide column stores, we saw that HBase, which is a wide column store, stores tables. Each table has so each row in this table has a row ID and arbitrary columns in column families. We saw the put command to insert a new row, get to find the row with a specific row ID, and a scan command to find rows between a specific range or find all rows, to scan over a set of rows. And the feature of HBase was very nice, called versioning, so we can store previous values of our columns to have a kind of history, and we can ask what the value was and when. For document databases, which store, for example, JSON documents, we took a look at MongoDB. MongoDB supports indexes and simple queries like the find command and complex queries with the aggregation pipeline. The idea behind the aggregation pipeline is similar to Gremlin. We start with all documents and then we only filter out those. We only want those that match a specific predicate. Then we group and then we unnest arrays and then we build arrays again and so on. So this is this one step after the other. And today we took a look at Neo4j. Neo4j is one graph database, and many graph databases uses the property graph model. So nodes and edges connect nodes, and both vertices and edges have properties and labels. To query languages, Cypher with this pattern matching approach, and Gremlin with this step-by-step pipeline approach for traversing the graph, going from one node that we start with. We know something, we know that the software is called Gremlin, and then we go to the people that develop Gremlin by traversing through the edges and the nodes of the graph. And now you can say in the job interview that you are an expert in NoSQL. Okay, you are an expert in NoSQL. Are there any other technologies you know well? The boss asks, yes, of course. No XML, no UML, no WSDL, no SAP, no IBM. Yeah. So NoSQL is good when you... How did we have it here? Do you have expertise in SQL? Then write NoSQL. Okay. I hope you learned something about databases which are kind of different than traditional relational databases. I will today continue with another non-relational concept, and this is called RDF. The slides about chapter 5 are online, and then in this chapter 5 I will come back to relational databases again, because yeah, Neo4j is a graph database, but you don't need a graph database to work with graphs. You don't need a document database to work with JSON data. We saw already that there's a JSON data type in many relational database systems. They, of course, have big benefits, and maybe they are more efficient and more comfortable to use and optimized for that. But it's also possible to do kind of all this with a traditional database. And there are new features like recursions in SQL, and we take a look at this chapter, but we do this in 2 weeks or in 3 weeks. Today I start with RDF. RDF is an abbreviation which stands for Resource Description Framework, and it is in W3C, this consortium that standardized web technologies. It's a standard, and it was made not only, but it was also made for the so-called semantic web. The web, we all know. We go to websites, go to Wikipedia, search something, read an interesting article, and then after this article, we know a lot of more things. This is how we humans work. We read a text and we know already some context. And this is very hard for machines. Machines don't have so many context information when reading a text. And this was the idea, to make the web more machine readable by annotating information on websites and in databases, on so-called knowledge databases. But let's start with websites. We have a website like a Wikipedia article. Let's go to wikipedia.org. Here's a Wikipedia article about DBpedia. Very, I wanted to say a very new thing in Wikipedia, but this is of course not new. A very popular element of Wikipedia are so-called info boxes. These were introduced some years ago on many websites. Let's go to a person. Let's go to Tom Cruise we had. Then we find also here an info box with a picture, and then born, occupation, works, spouses, children 3. So here's born. There we find when he was born. Let's go to another person. Let's go to Jim Gray. Database expert, also born, spouses. So you see, it's kind of consistent. So the problem in the normal web is often that you use different words for the same thing. Children, spouses. It was the same for this computer scientist as for this actor here. But this is not the case in general, because different people on different of different nations in different times collect knowledge, and one calls it children, other calls it child/children, in other it is called sons or daughters, and so on. So it is not standardized. And the idea of the semantic web is also to make a standardized ontology, it's called. Maybe you know the term taxonomy. Taxonomy is, let's say, eagle. Eagle is this bird. Do you call it a bird? No. Yeah. And the taxonomy is the idea to have a hierarchy of where it fits in. So an eagle is an animal and a class and an order and a family. So it's a hierarchy of, so this here is every animal, then those who can, I don't know what this is, I'm not a biologist. Then we have here birds, so those who have feathers or so and can fly. And then, so this is a taxonomy. Taxonomy is hierarchically. On the very top there is everything, then animals, humans, things, cities, virtual stuff, and then again sub things, so a hierarchy. And an ontology is a graph. So we are again talking about graphs. So how things can relate to other things. So an ontology describes the metadata to describe concepts. For example, persons, have, born, children, and what was the other, spouses, and so on. And there is a relationship between different things. For example, a person can be linked via an edge, spouse or child, with another person, or can be linked with a list of works. So here for Tom Cruise, this would be a long list of films where he acted. Yeah, actually this is not a list. This is an acts edge and another edge and another edge, all with the same edge label. So the ontology has the idea to standardize how things are structured and how they relate to each other. Here on the right I have one very small part of the ontology of schema.org. Schema.org is an ontology for very basic things. Schema.org/person, for example, says a person is a thing. Then this is a description, alive, dead, or fictional, blah. And then here are standardized properties. For example, birth date has the type date, and birthplace isn't, birth date is date, and birthplace isn't a string or something. Birth date is a relation, an edge to something of place. And schema.org/place is also a thing. And yeah, can have an address, text or postal address, and so on. So it's metadata that is standardized. Here I use schema.org/game to say game is a sub. Let's go to game. Is a sub thing of creative work. Thing, then creative work, and then game. And there's also video game, which is a subtype of game. And as you can see, here is also multi-inheritance. So video game is also a software application and a game. So it has both. So we inherit the properties from video game, like actor, on which platform does the game run, and properties from game. So these are the properties from video game itself. Then the ones which are inherited from the supertype game, for example, number of players, and then from software application, available on device, download URL. So we standardized a big set of metadata here. Number of players, publisher. Publisher is an organization or person. Comment is a comment. So the publisher can be an organization. And an organization is also a thing. Creative work is a thing. And the publisher can also be a person. Person is a thing. And person can have children, which are again person. So we are here now standardizing the metadata of a graph. Which node types are there? Game, person, organization, thing. Which properties are there for each node type? The game has number of players, blah, 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 blah. So this is an ontology that defines this. A classical website would look like this. If you would write this into a text editor, let's go to a text editor and I store it risk.html because it's a document, a website about risk. Risk.html. So the website would look like this. This is a very nice website that I, as a human, can understand. Risk is a board game by Hasbro. It was invented in 1957. This is a website like we know it. Maybe real websites are a bit more colorful, and but the idea is clear. We have information that's made for humans. Do you know Risk? That's a board game, and the one with a higher number on the dice wins. And the semantic website now looks like this. It looks extremely weird. Let's also put this here and I refresh. As you can see, I refreshed. It looks exactly the same because all information that I added here is added as attributes which are not visible for the humans. But these attributes can now help machines to understand the website here. So what is it about? So first of all, we use the schema.org ontology. And what we define within this div is type of a game. Property name we write here. Here we just used a human readable heading information. Now we say this heading stands for the name of the game. And then we write text. This is not so important, but here it is a game by, and then we define the publisher property. It is not like here a string. Here this property has the type string, risk game. Here publisher is a link to a different resource. And either this resource is also on my website, or I link to a resource or on another website or another knowledge base, and we will take a look at one big knowledge case called Yago in the next week, or maybe today in the last minutes. So we link to the information, okay, Risk is a game and it is by the publisher Hasbro. So if we want to find more information about Hasbro, we can go to this resource. And there we see, okay, Hasbro was founded in 1923 and so on. And Risk was invented in, and then the property date published, 1957. So what I did here was simply enriching a website's information with some tags, and these tags help machines to understand the web like we understand it. But this is now using a standardized ontology, a standardized dictionary. Okay, you could now say, who does this? Should I now, as a web developer, use these tags everywhere? I think nobody does this. This is an idea, but nobody uses these kinds of annotations. In Wikipedia, where we have these info boxes, which have also a standardized structure. A person has born and spouses and children. There is already a kind of automatic translation going on to transform these info boxes in such data here, in such so-called RDF triplets. And we can collect all this knowledge from Wikipedia and write a crawler and extract all this information. But there are already projects who did this, for example, Yago, DBpedia, Wikidata, and so on. What we have in the end is a graph. I will not call it property graph now. Here it's called property equal this, but basically a property in our graph is now an own node, and this this game node has now the property risk and the property publisher and the property date published, but actually these are neighbor nodes. So this is our risk game node, and then an edge name to a node that is so-called literal. We always have literals and resources. Literals are 1957. This is just a number. Risk game is just a string. And resources have a URL. http example.com risk game. That's like the URL that I used here. Yeah, that's a resource. But this here is also a resource. Schema:publisher. Schema: is a prefix which stands for schema.org/. So in RDF, often the people uses prefixes. So we define prefixes, schema: and it stands for https schema.org/. So this is a resource. A resource is a thing like risk, the game, or a predicate, schema.publisher, with a unique resource identifier. I want to know from you, please go to frage.space, how many resources are in this graph. Again, when 25 people answered, I show the solution. go to frage.de, frage with 2a, and show me the answer. So we have risk the game. This is like an instance, an object. This is not like game. But there is a resource for risk the game. And there is a resource for games in general. And there is a resource for edges. So basically everything is a resource. But not everything. There are also literal values. So 3 more answers. And then I show it to you. Let me count as well. Okay. Oh, 5 is the correct answer. Maybe when I explain a bit more about prefixes in the next slides, you know why it's 5. 1, this is a resource, risk the game. It has the URI, HTTP, example risk game. Then this is a resource, Jago Haspro. It stands for http jagoKnowledge.com jagoKnowledge.org/resource/Haspro. So it also has an URI, but we use here the prefix notation. And these here are also resources. schema.org/names, schema.org/publisher, and schema.org of date published or something. So 1, 2, 3, 4, 5 resources. These here are literal values. So 5 is the correct answer. Yeah, only 20% answered correctly. Yeah, most people said 7, but these are no resources, these are strings. Okay, the RDF, the Resource Description Framework, is a very simple idea. The idea is we use triplets, subject, predicate, object. Risk has the type game. Risk is the subject, type is the predicate, and game is the object. Risk was published by Haspro. Risk is the subject, predicate is a publisher, and then object is Haspro. So the RDF is a W3C standard to describe metadata and thus a major component of the semantic web. So the semantic web uses RDF. You can imagine an RDF store as a relational table with 3 columns: subject, predicate, object. And there you list facts. Facts about things. When a thing has 5 properties and 3 neighbor nodes, when we see it as a graph, as a property graph, then you have 8 rows or so. For all properties, literal value, and for all neighbors, also a predicate. So the subject is always a resource URI. The predicate is also a resource URI, and the object can be a resource URI. Then you can see it as a node to another, to an edge to another node, or the object is a literal value. Let me hide my webcam. So subject is the game risk. jagoKnowledge.org resource risk game. Then the predicate it uses, we could write RDF colon for this. So in the RDF standard, there is a standardized predicate called type. Risk has the type game. Risk has the publisher Hasbro. And Risk has the date published 1957 with the information that this is not just a simple integer, but a year information. So we can now ask, hey, how many years ago was the game Risk published? And then this helps us in answering this query. These resources, these URIs, are very long and ugly to read. That's why we use prefixes. And prefix declarations in the language Sparkle, which we will take a look at next week, look like this. We say prefix, and then we introduce a prefix. And these are the typical prefixes that are used for these ontologies here, or knowledge bases. So this is these are sources about metadata. So schema.org is a repository of full list of types, of persons, places, products, organizations, events, actions. So not so many things. So the basic things, therefore we can use the schema.org. And then this RDF, this has things like type. So these are very general things. RDF schema, there's for example this comment property who defines it. So this is all standardized. And the things which are not already standardized, for example, that there is a publisher called Hasbro, they are in this repository here, Yago. Yeah, and here's XSD. I used it for the year data type here. So this they simply reuse the data types from XML schema. Okay, at the rest we take a look next week. We will look at the knowledge base Yago and others. These are websites and projects that extracted automatically informations from the whole Wikipedia website and so on. And the nice thing is that these knowledge bases are not concurring each other, they support each other. So on Yago we see information about the game Risk, and then they have a link to DBpedia, a competitor of Yago basically. If you want to know further information, then go to the resource dbpedia/resources/risk game and so on. So the idea is to make a very big graph about all human knowledge. And then you can use it for Amazon Alexa and Siri and to ask questions and get answers. But we take a look at this next week, and we will take a look at the language Sparkle to work on this RDF data. Okay, but not next week. Next week is holiday, and we will have an exercise sheet and an exercise lesson this Friday. So we see us this Friday. The exercise sheet will be published, I think, this evening. Yeah. And then see you on Friday. Do you have any questions about RDF and crafts? Okay, then see you and have a nice time. Goodbye.